Thank you very much, Professor LeJunge and Mighty. Thank you for your invitation to give this talk. Hello, colleagues. Hello, everyone. It's my honor to have you all here. My name is Ben Ho Tong Minh, and I am a researcher from INRAE. My main research objective is to raise awareness on the importance of radar or SAR data to provide spatial information to better monitoring Earth's surface environments. So the topic today is how ground motion can be quantified from space by using a technique what we call the radar interferometry. So I will begin to spend a few words about the radar. So maybe you know already that radar is a really old technique that was developed about 100 years ago by a German engineer. Specifically, that is a signal transmitter and receiver system. So based on delays of the receiver signal, we can guess the distance from the radar system to targets. So this radar system can be on the ground, or for example, when we travel, we go to the airport, we can see that that's a very big antenna on the ground. It will be used to detect a certain target, like in this case, it's aircraft, to know how long it is to the airport. So that's exactly the radar system. And the radar system can be placed in aircraft or even on the satellites. Then, based on the radar signal, we can acquire the image on the land surface, like this one. We call this one is synthetic aperture radar. Synthetic aperture radar, or simply just SAR data. So the SAR data is the main actor of our story. Everything we do, everything we did, we use the data that contains distance measurements. The European Space Agency is pioneers on SAR satellite since 1992 with the satellite EIS-1 and 2, and then with the NBSAT ASA from 2003 until 2010. The original purpose was quite limited to scientific research, so very few images available for using, very few images available for doing application, and therefore very few people knew about it. In the past, when we're talking about SAR data, it's something like we're talking about something very fantasy. So it was not until 2014, and that's the new system, what we call the Sentinel-1 constellation, allow us to systematically capture the image globally, and especially that it provides it for free and open access. And since then, the number of the user has been explored a lot. Here, I will begin to explain how motion can be measured from space. So again, radar is the system that allows us to measure the distance from the sensor or the capture here and to the targets on the ground. So basically, that's, for example, that we use this one and we can measure the distance R1 like this one. So the distance from the antenna to the target on the ground is basically just a sum of many wavelengths of the radar system plus with its residue. So basically, we can think that using the radar is just like a ruler like this one to measure the distance from the capture to the target like this one. So the advantage of the radar of the satellite, so basically the advantage of satellite is that it can be go back to exactly the same position, sometimes with a little bit slightly different angle, and then they can do exactly the distance here if after a certain time, like 6 days or 12 days with the Sentinel-1 constellation, if there is a certain displacement on the ground, something like we don't know, a subsidence, earthquake, volcano, and so on, and that cause the target will be a little bit changing, and thus we can be able to measure the distance up to here. So accordingly, by taking the difference between the R1 minus R2 here, we can directly estimate the difference of the delta R, and delta R can be converted directly to the delta phase difference here, because we know that one lambda wavelength is corresponding to something like a phase cycle, either 2 pi or 360 degrees. So we call this phase difference is the interferometric phase. So with a wavelength of about 5.6 centimeters like C-band, like this one, the interferometric phase will be extremely sensitivity to any displacement on the Earth surface, because you see here 5.6 centimeters, just something like this one. So it is extremely sensitivity if there is certain displacement on the Earth surface. So the image contains that phase information. We call it interferogram. So basically, the idea of the displacement mapping is to we need to have one SAR image before and after a certain event, and then what we do is we try to compute the interferogram and try to quantify its phase difference, and that is the principle of the interferometric SAR data, or we call InSAR. Is this easy? So sometimes it's quite easy. This is the one interferogram. So it's quite one of the most famous interferogram in the world. So it's not the original, it's not the first one, but it's the most famous one. Why? What can we see exactly here? So it is really very beautiful butterfly. You can see here, like butterfly here, they have two eyes. One eye is open and one eye is closed. So winking and smiling to Earth. So she's really beautiful. But actually, the story behind this image is really terrible. Why? Because that is actually an image of the Earth's surface after a natural disaster, an earthquake. On exactly the night of December 26, 2003, there was an earthquake about 6.5 magnitude at a depth about 10 kilometers in the center of the Bam city, and that's a devastated the city and killed more than 26,000 people. So it's terrible. So in this context, many scientists have tried to contribute the relief to that disaster, and of course, in that case, there are also people from the InSAR science, and they try to use one SAR image before the earthquake and one SAR image after the earthquake, and they try to subtract it and form this interferogram. So, so what exactly inside this interferogram? So we know that this interferogram, so that's just image. So basically, that's just a matrix with a certain value here is corresponding to minus pi to plus pi. So a phase from minus pi to 0 to pi here, when the phase changing from minus pi to 0 and to plus pi here, we call this is corresponding to a phase cycle 2 pi. So basically, it will produce a fringe. It means when the color is repeat like this one. For example, when we have the blue at this one, and when it's going to so is it blue here? It's going to yellow, and it's going to red, and it's going to blue here. So from here to here is corresponding to 2 pi. So it's corresponding to one fringe, and the one fringe here usually that will be corresponding to a half of the wavelength. Like in this case, we're using the C-band of the NVSAR data. So its wavelength is about 56 millimeters. Half of wavelength is corresponding to one fringe. So that's why one fringe is equivalent to 28 millimeters. So, so we see here. So basically, in the interferogram, we see that the same color is just trying to repeat it from red to from red to yellow, to blue, and to red, and to yellow, and to blue, and to red. Just repeat it over and over again. So the concept of the fringe is actually very familiar with Earth in the context of the wood from the forest, wood fringe or in live fringe when after the raining, we can see that phenomena. So the earthquake, so now we try to quantify what exactly inside this interferogram. So the earthquake is basically that happened in the center of the city in this area here. So we know that in the center is the center part will be affected the most. So now we try to quantify it, what exactly the magnitude, the formation caused by the earthquake, and we assume that's about from here to about far away 10 kilometers here, the earthquake will be minimized. It means that the surface is stable or unchanged in the area of yellow color code here. So we see that from yellow here, when it go inside the center here. So we assume here is very impacted by the earthquake, so they are terrible here. And far away, about 10 kilometers, there's nothing even before and after the earthquake. So assume here is stable. So we try to use this one. So it's quite stable here. It's corresponding to the phase equal 0. So we assume nothing changed before and after the earthquake. And we try to use this one at the first reference point to understand what exactly the magnitude here. So what we do is we try to understand the pattern of fringe here. So here is the yellow going to the blue one and going to the red one. So we see here is the yellow going to the blue one. So it means from here to here, we see that the phase is decreased and it's repeat the yellow here. So from here to here, we got one fringe and the phase is decreased. So from here to here is one fringe and the phase is decreased. So just based on counting, just based on visualization, we try to count in the number of fringes and we try to quantify that magnitude. Because why? Because we know very sure that one fringe will be corresponding to 28 millimeter. So by counting number of fringes, so from here to here, we have 1, 2, 3, 4, 5, 6. So we know exactly that from here to here is 6 fringes. It will be corresponding something like 17 centimeter. And we know very well that the phase here is decreased. So from here to here, the phase is decreased. And how can we know that when the phase is decreased, it will be going down or going up? Can I say is it sinking or is it rising? So because in this one we use the image that the first before the earthquake minus to the one after the earthquake. So when the phase is going down, when the phase is negative, it means a subsidence. It means that when we assume that one is the preference one, and this one is going down until here, so that exactly we going down here about minus 17 centimeter. Okay, and what about this one? You see the pattern here from yellow to yellow, and it's going down, but yellow here, they go into red one, and they get to the blue one before getting to yellow one, yellow one here. So from here to here, we got one fringe, but the phase is changing 100%. Because why? Because here the phase is from yellow and they go to red one, yellow and they go to red one. So the phase is increasing. So from here to here, we got one fringe, but with the phase is increasing. It means that from here to here, the surface is changing, but it's rising about 28 millimeter. So again, we try to count in the number of fringes here. So from here to here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically that from here to the center of this one. So we know that we can count 10 fringes and the phase is going up. The phase is increasing. So we know that this one is going up about 28 centimeter. Okay, so that is a very special case of the interferogram, which allows us to easily quantify the the deformation caused by a natural disaster like this one is earthquake. But really easy, isn't it? But sometimes it's not the case. Why? Because this our satellite is something about very far from Earth, something about 750 kilometers. So the radar signal have to travel from space to the ground, and when it travels, the signal will be affected by atmospheric disturbance. And in that case, when we try to extract the signal to have the displacement exactly, we have to able to decompose the atmospheric contribution, and that is why over 20 years of development, many InSAR algorithms has been developed to improve the accuracy of measurement under that phenomena, under the atmospheric disturbance, and even sometimes like rapid variation. Because why? Because of course we cannot quantify, we cannot measure the displacement in forest area. We can do it, but at the moment in theory we can do it when we have very long wavelength, something like in the future we have the B-band from the mission biomass, which will be lost in the next 2 years. But at the moment we cannot do that. So what exactly the formula to show the problem of the atmospheric disturbance and rapid variation here is that we're not just using two images. We're not using two images, but instead of we use very long time series of SAR images all the time. It means that we not use just one, but we use many, 20, 50, 100, even 1,000 in future. So accordingly, that we are able to quantify that some target with very stable, like the tower, like this one. We call this guy very stable one. We call this one is persistent, with something like they have the characteristic persistent as a function of time. We call it that is one the BS point, and the other one we don't have a very stable property like the tower like this one. We call this one another one is the distributed scatterer. So sometimes we call it the DS here. So basically, that using a time series of SAR data, we can identify the BS and the DS, and the advanced algorithm, they just try to quantify based on the candidate, based on the BS or the DS, or even combine them together, and then using this one to remove the noise, remove the atmospheric disturbance contribution. So basically, they don't want to try to compute for the own target on the image, but just focus on the candidate where the good signals like the BS and the DS. So, so what do we have here? So we have the BS InSAR. Basically, that's one is very famous. Because why? Because the target, what we are considering here, usually that associated with the stable man-made structure, for example, the building, the bridge, and the tower. And it means that it's very good signal, and therefore the BS InSAR techniques provide very high resistance measurements and at stable positions. However, that's the BS technique is quite limited in when we go to our city. In that case, that the measurement point is not dense enough to see the whole picture, and usually that the people can combine. Now the people can combine that target with the distributed scatterer to combine to provide the better information in terms of the density and in terms of the accuracy also. So for the BS, the technique to do processing is S-pass baseline, something like we call it S-pass, that is the swan baseline subset. So usually that technique is usually they work directly on the unwrapped phase. So that's why it will be quite easy to implement, to do implementation. But they had a problem with the performance. The performance is not really high because why? Because they cannot quantify, they cannot track they cannot be sure that everything is perfectly for the whole image. So sometimes they will have a problem with the fade and wrapping, and whenever the fade and wrapping is wrong, it can be end up with, for example, end up with 28 millimeter wrong immediately. So there's algorithm already. So but we sometime nowadays we know that we are in the area of the big data. So there's a lot of data. There's a massive of data. So to work on that problem, we have to develop a certain efficient strategy processing, like the one in DS. We have an algorithm like sequential estimator, and for the one after the DS and DS methods, we have the one something like compressor data. So basically, that's a compressor data is just a technique to combine the sequential estimator and apply it into the domain of the DS and DS targets. So it's basically that it's just an InSAR compression technique, which is feasible for today big data era. So the algorithm already there, but we cannot calculate it by hand neither. Because why? Because it's a lot of work to do. We need a computer program to do that one. Usually that's as a function of time. We will find some tools, some software which is convenient for your application, or as a function of time you can build the one by yourself. And for me, I refer to the second approach. So that's why we have WGCapD like this one. So basically, as you know, over 20 years, there's many processor for time series InSAR processing have been developed. They have almost every software can develop SPAT. Because why? Because it's directly from the unwrapping phase. So that's easy because that's the linear inversion problem. And for the BS and the BSDS, they just took out to provider from TIE, that is company spin-off company from Politecnico di Milano, but it now is owned by the French Canet Space Agency. So and the WGCapD. So we trying to some illustration. So for the technique, we first started with BSI or the BS InSAR with the Mexico City here. So Mexico City, you know, that's actually the one of the most famous problem subsidence city in the world. Because why? Because of the magnitude. You see that most of the Earth surface happen for deformation in the world is about relatively low, about something like with the velocity trend, something like less than 10 millimeter per year, and very local, so something like less than 100 kilometers square. But with Mexico City, we see that the magnitude is a lot. It can go to the 30 centimeters per year, and it's in a very large area like this one. So we can see here, for example, that we can see if you play games, you can see that the pattern of the subsidence in Mexico City is something like a Batman shape. So it can be observed that with the center is something corresponding to 30 centimeters per year. So it's huge, it's a lot. And it's not really good for the human who live in there, because in the Mexico City is very, as the mega city with more than 20 million people living there. So it's kind of dangerous if people living there in unstable surface like that's one. And if we can write a certain profile from A to B here to appreciate how the changing of the subsidence at a function of the distance. So from here it's very stable, and we go into center. So we see here it's quite stable, and they can go to minus 200 millimeters per year. And you know that, for example, after 10 years old, we lost out. 1 year is 1 year is 20 centimeter, so 10 year is about 2 meters. So it will be a lot. So, and then 100 year, what happened? So of course, with that technique time series, we can even time travel, and it will able to tell you how's going on up the cloud moving from 2015. For example, we can see at 3 locations here. So upon 1 here is very stable, and going to a little bit medium up unstable, and very critical one like this one. So basically, with the technique of the radar interferometry, we're not only able to capture the trend of the velocity, the trend of the subsidence, but also we can able to understand what's going on as a function of time. And that's a very powerful technique. Because why? Because some application now, if you want to study some phenomena of the motion, you plan in something, but you can have only the measurement from now to the future. But with the remote sensing technique like this guy, like the radar interferometry, we can track to the bus to understand how it's going on as a function of time. For example, now 2021, and if you want, you can understand, okay, what's going on in 2016 and what's going on in 2017 and so on. So we're going to a little bit going to another test site. So this site is quite interesting because if you, for example, that is one is in Canfa, one in Vietnam. So this site is a very very big, kind of one of the biggest coal mining in Vietnam. Not only in Vietnam, but also one of the biggest coal mining in South Asia. So which has been exploited almost for a century. So there's a lot of problem of the subsidence over here. It's not really in grand scale. It's quite local. But you see here, for example, here in the mountain, the people try to mine in, and we see that with the classic techniques, and usually with just be a beside technique, we're just using the stable target. We're not able to detect this phenomena, but we're using with a certain advanced technique. We can see something here. And going to another test site, for example, that's on your left. We can see here this one is the Beauvais in south of France. So basically, the phenomena over there is the stock mining industry exploitation is usually here. So basically, that when they try to do exploitation, the sand over there, they have to inject the water, and they have to pump the water at high pressure into the wells. So basically, to dissolve the salt layer at the depth, and in that case, they can extract the brine. So basically, that brine will be used for the chemical industry, and this phenomena it happened from since 30 years ago. So basically, that and they will inducing subsidence of the surface. But if we use the classic technique like BSI, we have a quite a limited spatial coverage, so we don't know what's going on inside phenomena here. And usually in the past, people have to combine that performance with other measurement data, something like leveling, something like GPS station to do certain interpolation to understand the spatial coverage. But with advanced techniques, something like compressed data, which exploit many images together, put together, and exploit the BS and the DS, and they provide very useful information to know what exactly the phenomena here, and it will be provide the better data to do modeling to better management, for example. So we turn to the Mekong data for illustration. So Mekong data is here. We try to do a certain comparison between two algorithms. So the S-bar started the one from just doing with the distributed scatterer, and I used the one developed recently by the LISPAS toolkit, and the other one with the BSDS algorithm, so to combine techniques with the Tomusa platform. So basically that we see with using sophisticated platform, sophisticated algorithm, better results can be expected. Like we see with it's a better performance in terms of denser measurements. We see here this one we have a lot to understand how's going on with respect to this one. This one is also very good because why? Because a lot of stuff we can see a lot of problems we can detect here. For example, in Ho Chi Minh City, in Conquer, sometimes so we see the consistent between two rollers is in the big city. We see the phenomena is critical. Why? Because along the Mekong Delta, people just usually focus on a certain cluster like this one, very dense people living here, and not so much people living here because that's the urban field, and people living just along the canal and the linking part between province also. So let's close look to this product. So we see that this one is Ho Chi Minh City, and this one is Conquer, and this one is Camo. And do you recognize where is this? So basically that is the Phnom, the capital of Cambodia. So basically that's using the images, satellite images, that we can map whatever we want. There is no border at all. So here we are able to what do I want to share with you? That here we are able to map the whole Mekong Delta with a very large area. Like you can appreciate like 250 kilometers wide here and 350 kilometers along this direction. So it's a very big area. So in the past, when people try to map the certain phenomena in large scale like this one, in large area like this one, they have to combine many images together and do mosaic together. So in radar processing, we call up one incoherent processing. So basically, we do everything and we do mosaic together. Here, where with the Sentinel-1 data, is a very big one, so we can combine everything together in just one single image here, and we do a certain coherent processing and to provide the whole result, the whole results like this one. So we can focus on small area like this one to appreciate the performance of the processing in the Javan province. So we see here, so the population of the Mekong Delta is very evident here. So people to try to live along the roads and along the canals like this one. This one is the Wat Chan Po canal. It's complete just 5 years ago. So not so long, but you see a lot of people already taking place over there. So you can see here there are two die one through here. So the two dies were constructed just basically to try to protect the estuary here, and also they try to protect the bulk of this thermal power plant, because there will be a ship from the north of Vietnam, from the Vietnam, to take the coast. We go to here, and they will park in here, and then they will do some logistics to take the cost for this thermal power plant. So we see here, we want to, if we zoom in on this one, and we see even how's going on, not just one single value, but the distribution of the spatial in terms of spatial information, to appreciate how it's unstable. So we can even travel to see how the displacement has been progressed since 2015. So I try to recall and try to remind you that the satellite is about 750 kilometers from the position we are surveying in here. So with the equivalent to the distance from Saigon or Ho Chi Minh City to the Bangkok, Thailand. So with such distance, and we have the ability to identify and track the deformation at a certain millimeter scale like this one. And this one is one of the amazing things about the InSAR technology. So we can map Thailand for a very large region like the one you see in Mekong Delta. So to do validation, it's kind of typical stuff. And we consider here a strategy by comparing the result of when we consider very large delta Y like this one, and we try to compare when we do the processing for small area like this one. So we go back to Ho Chi Minh City to do more detail. So we do exactly the same thing for the Mekong Delta, but just crop the image, just focus on Ho Chi Minh City here. So we do exactly the same processing, but in Mekong Delta, we take a very large area. So there's some tricky problem we cannot show is very consistently. But for a small area, it will be faster and it can be robust and it can be easier also. So we try to compare the small resin velocity, so small resin trends up the surface, and then compare it with the large resin velocity. So this one is from Ho Chi Minh City, and this one is from Mekong Delta. We put it together, and to see that has yon, and you see that they're quite exactly the same. So that is one cross distribution, and it's showing that it indicates that it's quite identical spatial distribution with less than 1 meter per year difference of velocity. So it's good. So it means that even we go into large area for the whole Mekong Delta, we can do processing and in the way that it's very reliable and very robust for even a very large scale like this one. So we try to appreciate the results in Ho Chi Minh City. It's available online if you want. You can download it freely. So here we try to appreciate this zone because this one is very critical in Ho Chi Minh City. So you see in Ho Chi Minh City in the inner of the city. So in our city, it's quite stable. It's just green, so it's stable. The rest is quite unstable. We focus on this one and we try to capture on this one based on 3 different SAR data. So we see that the difference, but they say the same data. They are different data show. So this one is from exactly from the same one data, but this one ascending, and it means that the satellite is going from the south to the north, and for this one is from descending. It means that the data is going to the north to the south, and the other one is another satellite from the Italian space agency, that we call it Cosmoscanet. So even 3 data show like this one, they share the same spatial distribution. Of course, if we go into a little bit detail, like this one, that's profile along the Nguyễn Văn Linh street, and we see that if we go into detail, that they will be a little bit different, but it's very tiny. So of course, that even if we try to focus on a certain point, we can time travel as a property of the radar interferometry. So we from here in the current, and we travel to the bus to understand how it's going on. So basically, that's the problem of the displacement, the problem of subsidence, the problem of deformation in Ho Chi Minh City, and in many cities in Mekong Delta is quite linear. So we take a closer look at one of the famous area in Ho Chi Minh City. So have you noticed that So this is the zoo, and this is the Saigon River Bridge. So, and this is the Van Tan. So close here we have a metro station, which already done for construction. So we see this area is very famous for the problem, for two problems. The first is flooding. I mean, whenever it comes to rain, and it automatically get flood. Not this one, sorry, this one. So this one is Nguyen Hữu Cảnh. This one you see here. So this one Nguyen Hữu Cảnh. So, but the problem is very famous for flooding. Whenever it rains, it's going to flooding. So because it's that's problem. So the street is often try to build again. So they increase the elevation. They will rise a little bit higher as a function of time, and then leading to many houses nearby here. They almost nearly to lower nearly about 1 meter. So you see, you understand here, like here, like the street here is higher than the house nearby 1 meter. It means that when there is a heavy rain, so basically that the house living here, they become something like the water town. So a lot of water, like a river inside here, everywhere is become a river when it's rain. So and also it's easy to recognize that this area is not really stable, and because that problem, and that's why people have to try to maintain and increase the elevation to deal with the subsidence also. So we back to our capital in Hanoi. So in Hanoi, that they have they said the risk of subsidence, because that risk has become increasingly frequent in Hanoi recently. Because why? Because of there's a problem of the urbanization. So people have to try to extract the water from the crowd beneath to meet the living. So we see here that for example, one data recently we use for the image from 2015 to 2020, and we can able to capture the subsidence in Hanoi. So basically that's in along the north west in the south of Hanoi, so basically in the south. But the magnitude is very small with respect to all the city, like in Mekong or like in Ho Chi Minh City. So basically that the phenomena is the same, but the magnitude is a little bit minor. So why we have to focus on this data? There's a hit. Because you know what that we want to understand now the problem. What is exactly the problem? You know that Vietnam is located in the tropics, so where the conditions are affected by very strong interference disturbance, and we want to demonstrate that is feasible, and we are able to determine the subsidence even using the X-band in the critical problem with the interference line in the north of Vietnam, line in Hanoi. So why do we use the SAR? Because that is better to understand the potential science of the future Vietnamese satellite. So, and that is have strong implication for our mission. So we have the LOTUSat one, that is the Vietnam SAR mission, which is expected to be launched about 2023-2024 timeframe. So basically that are we ready to explore that data for future potential application? It's the hope that we can build a certain community to exploit that data, and we're ready for that one in future. So we already demonstrate that X-band it works very well in estimating ground subsidence in Ho Chi Minh City, in Hanoi. And also we also provide a strong support for scientific potential of X-band spaceport mission in Vietnam. And even that the atmosphere is in Vietnam is very strong, but it can be done. So what do we do next? So what we do, I'm happy to let you know that I will offer a free 2 days InSAR tutorial in 2022. So I try to do a little bit survey, and people very happy with a certain person online. So I will let you know very soon. So if you have a BSD scholarship and you want to do in InSAR, welcome to my club. So I hope that you can do with me after 3 years, you can be able to finish the BSD. And finally, if you want to have more information on radar interferometry, you need to research or have something you want to share, just follow us in YouTube and Facebook. Thank you for your attention.